Hey all, I hope you are doing well. In this video, we're going to take a look at Bitcoin, one of the most interesting technologies of our era. I think it's a worthwhile exercise to really understand how it works under the hood. And one of the most interesting resources to do that is the book Mastering Bitcoin by Andreas Antonopoulos, which is really a tremendous book by a remarkable author that I highly recommend. This video is my summary of it after having read it. So let's dive right in. So Bitcoin is the first successful digital money. This begs the question, what is money? Money, there are two definitions I like very much. The first one is money is economic energy that flows through space and time. So if you work and transform that work into money, into wages, you can spend that money in the future, tomorrow, the day after, or in different location. So it flows through space and time. Another way to look at money is as the ultimate medium of exchange. So we need to exchange different goods and services, and money is the most liquid good that can always be exchanged for other goods and services. And Bitcoin is the first digital successful form of money. It is decentralized, so there is no central authority or entity controlling it. It is trustless, so it doesn't rely on trust of any third party. So let's take a 10,000-foot view of what Bitcoin is. It is first and foremost a protocol. It is a way for multiple nodes on a network to communicate and agree on a current state of affairs. So there are various implementations to the protocol. So the reference implementation is Bitcoin Core, but you have other implementations in Golang, in Scala, even in JavaScript. And there are a large number of nodes currently running the Bitcoin protocol and participating in the Bitcoin network. As we can see here, there are currently, as I am speaking, 23,537 nodes participating in the Bitcoin network all across the world. And we can even look at the map. So what does the Bitcoin protocol specify? What does it represent? Bitcoin at its core is a list of transactions. Every 10 minutes, a group of transactions is bundled together into a block, and this block is linked into the previous blocks, forming a chain of blocks or a blockchain. So every 10 minutes, all the nodes participating in the network accept transactions and put them in blocks, and there's one block that's gonna emerge and be chained to the rest of the blocks, forming the blockchain. When I hear this definition, three questions come immediately to mind. The first one is, how can you make sure that your Bitcoin, that your money is not stolen if everybody has the same blocks and the same transactions? And the answer to that is asymmetric cryptography, private and public key pairs. And we'll talk more about that later. The second question that comes to mind is, how do all these nodes agree exactly on the same blocks? Because we saw there are more than 20,000 nodes running currently, and a lot of new transactions coming in. So how do we make sure that they all agree on the same list of transactions and blocks? So this is the main and the most innovative idea that came out of Bitcoin, and it's called proof of work. So this is how it goes. Each node in the network is running constantly a mathematical function, which we call a hash function. So a hash function is a function that takes some input and always produces the same output for the same input. And if you change the input, the output changes. And it produces a completely random number. So in the case of Bitcoin, we set a target and we say that in order for a node to successfully add a block to the chain, the output of its hash needs to be smaller to a certain value. So something I did not tell you is that the hash function can produce a value between 0 and 2 to the power 256. So that's 1 followed by 77 zeros. That's like a few zeros shy from the number of atoms in the universe. So that's how big the hash function result is. And the target is a smaller value. It's like saying pick a random atom from the whole universe, and this atom needs to belong to a specific planet or a specific country. It's you have all this huge space of values and you constrain the target to it. And it's all random. So whenever a node comes up with a value that's lower than the target or that belongs to that constrained space, it proves that they did a lot of trials, millions, trillions, gazillions of trials. So this, by doing this, they proved their work. So proof of work. So based on the current number of nodes in the network, based on the current computing power participating in the network, the target difficulty is adjusted, and we are sure that on average, probabilistically, only every 10 minutes, a node will be able to successfully find a correct hash. And that's how we ensure that all the nodes agree on the same value, on the same view of the blockchain. They reach their consensus. Third question is, why would a node participate in the network? And if it did, why would it pick transactions by this user or not that other user? Why would it have some preference to certain transactions? What's the incentive behind all that? And the answer is mining in fees. So the process we just explained of finding the correct hash, so you have the number that's below the target and you proved your work and you expanded enough computing power and energy. When you succeed, you are rewarded by the ability to create new Bitcoins from nothing, ex nihilo. And in addition to that, each transaction that users make, they add a small addition to the money they're paying to the output in their output. And that small difference is a fee that can be claimed by the node that successfully mines and wins the every 10-minute lottery. So these transaction fees plus the ability to create new Bitcoins is the incentive that keeps mining nodes and nodes participating in the network. So Bitcoin nodes communicate over the internet. So that's an interconnected network of computers. But it is absolutely possible to have a run of Bitcoin in a private network, and nodes would be communicating within that private network. So the internet is just convenient. You could think about a version of Bitcoin running only in constrained geographical location, such as a specific country or maybe a new planet in Mars coin. And yeah, so one of the key ideas in Bitcoin is that there is a fixed amount of Bitcoin. So miners create new coins by adding blocks to the blockchain when they win the mining contest or lottery, depending on how you look at it. And the number of generated coin per block continuously decreases, and at some point it's going to be zero. So there will be a point in time, approximately in the year 2140, where there will be no new Bitcoins generated. And this means that the set of Bitcoin is limited, and it's limited to 21 million Bitcoins. And this means that as time progresses, the value of Bitcoins would not be subject to inflation because the supply of currency did not increase, but rather to deflation. And that's what we mean when we say that Bitcoin is deflationary. So um, the Bitcoin paper was published in 2008 by Satoshi Nakamoto, which remains still to this day anonymous. It outlined the principles and the protocol, and in 2009, Satoshi published an implementation of the protocol, and it started. The Bitcoin network started, and Satoshi was in the picture until 2011, at which point he withdrew, and Bitcoin was maintained by a group of volunteers. So the code is open source. You can look at it in GitHub or with the various implementations, and nobody has control or the ability to tamper with it because it's all based on this decentralized consensus. So you can have different types of nodes participating in the network. You can have the full nodes who have a complete view of the network and that validate all transactions and all that. Or you can just have lightweight nodes, which only care about a subset of transactions for certain users or only do some specific operations, not the whole 9 yards. Andreas, the author of this magnificent book, coined the phrase your keys, your coins. Not your keys, not your coins, which basically means that the private key that you need to unlock and spend your Bitcoin must be in your possession. If it's handled by somebody else, you're probably not 100% safe. Uh, so all this feels a bit too abstract until you really give it a try and send and receive some Bitcoin and see how it feels. So I did just that, and the way I proceeded is I installed this Electrum wallet, which is a wallet like many others that holds your private and public keys so you can receive and send Bitcoins. And it has a very simple installation process. Then I generated a public key. So it's very simple. You just fill in the description of the transaction. And all this is optional, the requested amount. So this is merely Bitcoins, 1,000 of Bitcoin. And you generate an address and it spits out this QR code, which is basically just a public key address and the amount. And using my Robinhood trading app that offers Bitcoin transactions, I scanned this QR code and sent some Bitcoin. So I waited a few minutes and then I received this email by Robinhood telling me that my Bitcoin has been sent to the address I specified and it gave me a transaction ID. So if we take this transaction ID, so we take the transaction ID and we go to this website called Mempool Space, which is basically a web interface to view what to take a look at the blockchain. So I copy the transaction ID and I look at it and I can see that an input of 105 Bitcoins has been sent to multiple addresses. We'll take a look at what that means later. And if I look for my public key, I can see it here, and that's 8,507 Satoshis. And let's go back to Electrum and take a look at the list at my history. And here it is, the same transaction. And the two are completely separated, but they share the same database, which is the blockchain. And I can indeed find the same transaction ID and see the public key address I used with the same amount, 8,507. And yeah, that's pretty cool. It really shows you what actually happens behind the scenes.
So As we discussed, in Bitcoin, there is no trust in third parties or any central authority or entity, and that's key. Each user can verify all their transactions and any other transaction either by running the software locally on their own node or by checking one of the various websites that offer a web view of the blockchain. Blockstream, Mempool, lots of popular options. Buying from an online store is as simple as scanning a QR code. So the online store generates a QR code that is simply an invoice that has the destination Bitcoin address where the money needs to be sent and the amount. The label and the description are only useful for the user's wallet. Those are not included in the blockchain. So, a Bitcoin transaction is a certified way to tell the network that the owner of some Bitcoins want to transfer ownership to some other recipient. The new owner can then create their own transaction based on this previous transaction to pass those coins along. And this goes on. This is very much like a $10 bill traversing the economy from person to person. The Bitcoin transaction maps inputs, which are actually outputs from previous transactions, to new outputs, which are the destination addresses, i.e., the public keys of recipients. So you can have multiple inputs that reference previous transaction outputs mapped to new outputs, the recipients of these inputs. The outputs total slightly less than the inputs. The difference is the fee that can be claimed by miners. This fee is what actually incentivizes the miners to include transactions in their blocks. Otherwise, why would they? So, fees are important. And actually, the busier the network is, the more transactions are waiting to be confirmed, the higher the fees. And so, if you want your transactions to be quickly confirmed, you pay high fees. Each input in the transaction must be signed with the owner's private key. The signature is public, but only the owner can create it. So in the previous output, we have the owner's public key, and only with the corresponding private key, we can provide a signature that certifies ownership. Transactions are chained. So as we can see, the output of TX1 is referenced by the input of TX2, and that's the TX1 colon 0. That means the output at position 0, and so on and so forth. And so each transaction is part of a transaction chain. So oftentimes the inputs don't add up exactly to the output. So imagine I have 1 Bitcoin from a previous output and I want to send only 0.2 Bitcoins. How am I going to do that? Because I don't want to send them the whole input. So the inputs need to map up to the output. So the way we do this is by making change, very much like we make change with normal money. So we create a second output of a public address that I own, and I send the change to that public address. So I have the inputs plus the desired outputs, and the change is sent back to an address owned by the original owner. And we don't forget about fees, of course. The actual unit used by the Bitcoin software is 100 millionth of a Bitcoin. So 100 million units give us 1 Bitcoin. And this did not have a name at first, but was later named as Satoshi in honor of the Bitcoin's creator. So when we say Satoshis, we mean that 100 million Satoshis give us 1 Bitcoin. Uh, the, so there are different forms of transactions depending on the type of inputs and outputs. So we can have a common transaction where we have one input and we send it to one output and the change is sent back to the owner. That's a common simple transaction. We have an aggregating transaction where we have multiple small inputs that we send to one big output. This could be a way to clean up the different small previous small outputs. And we have a distributing transaction, which is simply a big input that's distributed among multiple smaller outputs. This is actually just a way of organizing things. The main idea is that you can have one or more inputs and send those to one or more outputs, and then you organize this according to your needs. So, how is a transaction constructed? First of all, we need to know the destination public address. We need to know to whom we're sending the transaction. And only the owner of the private key corresponding to that public address will be able to spend the notes by proving ownership through a signature. So once we construct the transaction according to the protocol format, we forward it to nodes in the network, and a miner, seeing that we are paying some interesting fees, will include this transaction in a block and start mining, looking for a hash so he can confirm the block and get his reward plus the fees, and the block will be added to the blockchain, and so is our transaction. So the network is peer-to-peer, meaning that you have equal peers all participating in the network, and each peer is also called a full verification node because it has a full copy of the blockchain and it can verify all previous transactions, that the outputs indeed exist, that the public keys are all good, the format are valid, and all that. And the transaction can actually be sent to any node participating in the Bitcoin network. And then if the node sees that the transaction is valid, it will forward it to other peers. And those peers will do the same. And in no time, usually a few seconds, the transaction is propagated through the whole Bitcoin network. And let's be clear, to send Bitcoin, we do not need any other information than the recipient's public key, and that's it. So let's keep in mind that propagation through the network does not mean that the transaction has been added to the blockchain, because as we said, it needs to be mined in a block and then added to the blockchain. And this process happens every 10 minutes approximately on average. So as we said previously, the miner will receive a group of transactions, it will hold them in its mempool, and it will take the transactions that are the most lucrative, meaning having the higher fees, and bundle those in a block and start running a computation to find the result of a hash that's inferior, that's less than the current target. And as we said, this operation is extremely compute intensive. This is like running trillions and trillions of computations trying to find one atom in the universe within a single planet at random. This is how hard it is. And so once the miner finds that hash that's less than the target, they have proved that they've done some work, and they can mine new bitcoins. As of now, it's little over 3.1. That's more than $300,000 at the current exchange rate, which is, for 10 minutes of work, a pretty nice reward, plus the different transaction fees. And the mining node propagates the block to the other nodes in the network, and they add it to the blockchain, and our transaction is confirmed. It is usually advised to wait for more confirmation before actually considering the money received, because although it's uncommon, it can happen that two blocks are confirmed at the same time, so two miners find hashes at the same time, and each will build on their successfully mined block to find another one, and the longer chain wins. So after three, four, five confirmation, it's very unlikely to have competing branches. So that's why it's recommended to wait a few confirmation to be 100% sure that the transaction has been confirmed. And yeah, that's it. Once the transaction hits the blockchain and it has some confirmation under its belt, the recipient, using their the private key corresponding to their public key, can sign a new transaction, and a new adventure of transaction propagation confirmation begins. Yep, as simple as that.
Okay, so as we already said, Bitcoin is simply a specification. It is nothing more than a protocol. And there are multiple implementations for this protocol. The reference one, the most commonly used, is Bitcoin Core, implemented in C++, but there are multiple other implementations. Notably, there is the Golang implementation BCTD used by Lightning Network daemon LND, but there are also implementations in Scala or JavaScript. It's quite simple to download the source code of the Bitcoin Core repo, clone it from GitHub, then run the build script. Although building large C++ application has its challenges, so the architecture looks something like this. So a lot of bits and pieces, DSP discovery and connection management. There's also components to manage the wallet software, to create transactions and manage public and private keys. We can also see the storage management to store blocks, coins, a minor component. Very interesting stuff. So once you clone the repo when you build it, or you can just download the executable, you can start a Bitcoin node using the Bitcoin D command. And it looks something like this. You can run it, and it also has a lot of options. So you could specify an alert notify option to be. This could be a script that sends an email or Slack message to be notified of certain stuff. You could also specify the data there, which will indicate where the blockchain data will be stored on the node. Could specify the prune option to get rid of unused blocks and save some space. Lots of interesting stuff. So in this chapter, we're not going to actually download the code and download the blockchain because it's just too much and it's going to take too much time. So I found this very cool website, Chain Query, which exposes Bitcoin CLI through a web interface. And they have a node somewhere that has the blockchain, and they're exposing the Bitcoin CLI through this web interface, which is pretty cool. So one very cool command is get blockchain info. There it is. And yes, we are not a robot for now. So let's run this command. And it basically gives us the state of the blockchain on the node as we speak. So the chain is main. So this is to differentiate it from test chains and stage chains. There are different types of chains, but they are basically used to develop new versions of the Bitcoin software and test upgrades and stuff like that. We'll get into that later. So there are currently 909,000 blocks, so almost a million. We can see the target, which is what we spoke about earlier. We talked about the mining difficulty. So the hash function resolve needs to be less than this for the block mining to succeed. We can see the time. We can see also the size on disk. So the blockchain on this node is currently taking up to 800 gigabytes, which is a healthy size. So let's take a look at another command. So one useful command is get row transaction, which given the transaction ID, gives us the information about this transaction, fetches it from the blockchain. So I'm going to use the transaction I demonstrated earlier by sending money to from my Robinhood account. Let me fetch that transaction ID. So I have the transaction ID, and let's set the output to verbose and show again that we are not a robot. And we get the output. So this is the transaction. You can see the transaction ID, it's the same. And the VIN, it's the transaction inputs. And we can see that we are using input from another transaction. So this input is the output, is referencing an output from a previous transaction, and it's this transaction, an ID, and it's output number one. So if we go look at this previous transaction in another get row transaction, we look at the output number one. So this is the input that our transaction is spending, and it has a value of 105 Bitcoins. And if we go and take a look at Mempool and look up our transaction ID, we can find the input we are indeed spending, and its value is 10 billion and 500 million Satoshis, which equates to 105 Bitcoins. So that's cool. One final thing I want to do is our transaction is part of a block, and a block bundles multiple transactions together. And the CLI lets us query a block. So there is this neat get block function. And if we provide the block hash, we can see all the transactions that are part of the block. We can see its target and a lot of interesting information. The confirmations, how many blocks have been confirmed since this block has been confirmed. The Merkle root, that's something we'll look at later. Lots of interesting stuff. So yeah, that's pretty much it. So this concludes the chapter, but also the video. Thank you very much for making it this far. I hope it has been informative, and thank you for watching. Goodbye.